So we'll start today by writing a rule for this sequence. Remember, we can write sequences as an explicit rule or a recursive rule. Some sequences can only be written with recursive rules. Some can only be written with explicit rules. It really depends on the problem, depends on the context that you're looking at, and depends on the sequence. This particular sequence, we're going to write a explicit rule for. So an equals something. Now, sometimes these rules, you got to do some thinking to figure them out. They're not just going to become immediately evident. With this, I notice that it's a fraction. So I know that I'm going to need a fraction. And what do we notice about these numbers? So 1, 2, 3, 4. Let's look at the numerator separate from the denominator. Well, these are just the values of n. N equals 1, n equals 2, n equals 3, n equals 4. So it seems like I can put n as the numerator. This is term number 1, term number 2, term number 3, term number 4. The next one would have 5 on the top, and it's the fifth term. Now, where are the bottom numbers coming from? Well, the bottom numbers, 4, 9, 16, 25. This next number, I'm going to go ahead and venture a guess that it's 36. These appear to be a progression of the perfect squares, but it's not 1 squared, 2 squared, 3 squared. This is 2 squared, this is 3 squared, 4 squared, 5 squared. It's the next number squared. So for term 1, we're squaring 2. For term 2, we're squaring 3. So what we're squaring is our n plus 1. And here is an explicit rule that generates this sequence. If I wanted to know what the 100th term was, A100, it would be 100 over 101 squared. And there we have it. There's our rule. Sometimes they're a little bit more tricky than others, but you just have to look at the different parts of the sequence, the different parts of the terms, and try to figure it out. As we move forward, we'll see some sequences that follow very special patterns, and we'll be able to write rules much quicker. But the big idea for today is sigma notation. This big E-looking thing, it would be the capital letter sigma from the Greek alphabet, and what it means is add stuff up. It's about as far from a formal definition as you can get, but mathematically it means add up a bunch of stuff. So there are three main parts to sigma notation. We have something that comes right after it, and that's the explicit rule for generating the terms of the series. So our rule is just plain n. And then there's a bottom number. The bottom number is the first value to substitute into the rule. If you will, it's the starting term number. And then there's a number on top of the sigma that's the last value to substitute into the rule. That's the end term number. So what would this expansion look like? Well, we'd start with 2, plug it into the rule, we get 2, plus, because it's sigma, 3, plus 4, plus 5, and we stop there because that's the last value of n that we plug in here. This means start by plugging in 2, continue to plug in integer values of n until we hit this stop value of 5, and we could combine this together and say that this summation, it's called, this series is equal to 14. So before we go any further, what is a series? Series, you say? What could that be? Well, let's back it up and talk about what a sequence is. A sequence was a list of numbers, simply put. Usually there's a rule that goes along with them that we get by plugging in successive integers. But a series is the sum of a sequence. So if I have a sequence and I have a bunch of terms, if I put pluses in between all of them instead of commas, now it is a series, and I can add those values up to get a final sum. So let us look at this example. we have the summation from k equals 1 to 4 of 1 plus 2k. So what does this mean? Well, what's the 1? Think about that. That 1 is the first value that we plug into the rule. So our first term is going to be 1 plus 2 times 1. And we write plus because it's a summation. The next value of k would be 2. So 1 plus 2 times 2. Plus the next value of k, 1 plus 2 times 3. And finally, 1 plus 2 times 4. And this is where I stop because I've hit my maximum value for k. And now we simplify this to become a term of numbers. So 2 times 1 is 2, plus 1 is 3, plus 5, plus 7, plus 9. We add this together, we get 24. So this series, this summation, is equal to 24. We could think of this as having a rule, an equals 1 plus 2k, and we just wrote out what a1, a2, a3, and a4 are. 3, 5, 7, and 9 respectively, and then we added them together to get the sum of this series. Remember, the big sigma means sum. Add up all the terms. And there we have it. There's a brief overview for what a series is and how we use sigma notation. Just to revisit this right here, important stuff. You got to know what the 3 pieces of sigma notation are.